The origins of the asteroid that killed the dinosaurs, a 66 million year mystery unraveled. 66 million years ago, Earth had what could be called the worst day in its history. An enormous asteroid, traveling at a speed of several kilometers per second, slammed into what is now the Yucatan Peninsula in Mexico. The collision was so powerful that it released energy equivalent to 100 million nuclear bombs. The impact left a 200-kilometer wide and 20-kilometer deep crater known today as Chicxulub, triggering a global cataclysm. The immediate aftermath was devastating. The impact generated colossal earthquakes and towering tsunamis. Firestorms raged across continents, setting vast areas ablaze. But that was only the beginning. The impact ejected immense plumes of soot, ash, and vaporized rock into the atmosphere. These planet-smothering clouds blocked sunlight for years, causing a drastic drop in global temperatures. Photosynthesis ground to a halt, and food chains collapsed. Over 75% of all species, including the mighty dinosaurs, were wiped out. The world became a wasteland, but from this destruction, new life would eventually emerge. For centuries, the cause of this mass extinction remained a mystery. Then, in the late 20th century, a breakthrough came from an unlikely source, a thin layer of clay found in 66-million-year-old rocks around the globe. Physicist Walter Alvarez and his colleagues noticed something peculiar. This layer was enriched with elements such as iridium, an element rare on Earth but abundant in asteroids and comets. The evidence pointed to a massive extraterrestrial impact. They connected this iridium-rich layer to the Chicxulub crater, naming it the Crater of Doom. The mystery seemed solved, but questions remained. Was the impactor an asteroid or a comet? And where did it come from in the vastness of space? Decades of research and debate followed. Some scientists suggested the impact could have been caused by a comet or even by massive volcanic eruptions spewing iridium from within Earth's mantle. But a groundbreaking study published in 2023 offers the most definitive answers yet. By measuring isotopes of ruthenium found in the debris of the impact, scientists have been able to pinpoint the source of the asteroid. Ruthenium, like iridium, is rare on Earth's surface, but common in extraterrestrial objects. The study shows that this ruthenium is not from volcanic activity, but from an asteroid, a specific type known as a carbonaceous asteroid. These asteroids, rich in carbon and organic compounds, originate from the outer regions of our solar system. Carbonaceous asteroids are relatively rare. They are thought to have formed beyond Jupiter before being hurled toward the inner solar system by the gravitational influences of the giant planets over 4.5 billion years ago. These asteroids are believed to have brought vital organic materials and water to early Earth, playing a key role in the development of life. Ironically, the very process that helped kickstart life may have also set the stage for the dinosaurs' demise. The study's lead author, Mario Fischer-Gode, and his team used a technique called multi-collector inductively coupled plasma mass spectrometry to analyze 7 different ruthenium isotopes from samples collected around the globe. By measuring these isotopes and comparing their ratios to those expected from cosmic processes, they were able to conclude that the impactor was indeed a carbonaceous asteroid. This discovery effectively rules out other theories, such as volcanic activity, providing the nail in the coffin for the asteroid hypothesis. The study also raises questions about future impacts. If a carbonaceous asteroid like Chicxulub could wreak such havoc, when might the next one strike? Scientists estimate that an impact of this magnitude occurs once every 250 to 500 million years. While the odds of another such event happening soon are low, continued vigilance is crucial. The new findings have stirred discussions in the scientific community. Steve Desch, an astrophysicist from Arizona State University, finds the evidence convincing. He notes that it aligns well with other geochemical studies of impact debris. Other experts, like Richard J. Walker from the University of Maryland, emphasize that while the conclusions are not entirely new, the precision of the isotopic measurements is groundbreaking, providing a more ironclad determination of the asteroid's origins. James Day from Scripps Institution of Oceanography highlights that these stellar nucleosynthetic variations in isotopes give us unique insights into how different parts of the solar system evolved during its early formation. The study also brings to light the complexities of tracing cosmic material across billions of years, from its formation in supernova explosions and star interiors to its journey through the solar system and eventual collision with Earth. Lead author Mario Fischer-Gödde is optimistic about future research avenues. He suggests that examining additional isotopes from comets, lunar craters, and other sources could refine our understanding of the solar system's history and the events that have shaped Earth's biological evolution. The story of the Chicxulub impact is more than just a tale of destruction. It's a cosmic story that connects the origins of life to the death of the dinosaurs, demonstrating how events billions of years ago can shape the world we live in today. As we learn more about our universe, we uncover not just the history of our planet, but the intricate dance of celestial bodies that have written the fate of life on Earth. For more insights into the universe's greatest mysteries, subscribe and stay tuned.